Hello? Alright, cool. So they can hear us.
How did you have it set up when we were doing this?
The oh yeah, I just had that. Well, since they're using projector, I put it here because I was using the board.
You need to write stuff.
Oh, you need to write stuff.
Yeah.
I have markers. Alright, so we are live. That's good. You can see yourself here.
Yeah.
Use this. Then 2, 3.
Here's an answer. Thank you.
That doesn't die.
Since I can't really see,
Yeah.
maybe I just don't use that. I just read the problem.
Yeah, sure. That works too.
Give me 1 second. Let me just get the problem up here.
I'm gonna join on my phone just in case I gotta leave.
Alright, I'll probably start now. Alright, so today I'm gonna be going over a problem called Treasure Maps. It's from ICPC Regional Contest for South Division from 2017. The problem statement goes as follows. You have a treasure map. The map leads you to several gold mines. The mines each produce gold each day, but the amount of gold that they produce diminishes each day. There are paths between the mines. It may take several days from one mine to another. You can collect all the mine's golds from a mine when you are there, but you have to move on. You cannot stay multiple days at the same mine. However, you can return to the mine after leaving it. So the input will consist of a single test case, N and M, where N is the number of mines and M is the number of paths. Then you're given N lines, where G and D, G is the amount of gold on day 1, and D is the amount of gold by which the haul diminishes each day. For example, if G is equal to 9 and D equal to 4, then on day 1, the mine will produce 9 gold. On day 2, it produces 5, and so on and so on. Then you're given M lines, where each line consists of a path from mine A to mine B, and then it takes T days to traverse from A to B. This path is bidirectional, so it doesn't have a direction on each mine. Let me see. This stop. Okay. And how do I bring this up, Lazaro?
The projector?
Yeah.
Yeah.
Off?
Yeah.
Awesome. So I'll just write the input right over here. So like I said, N and M. Can you see that? Is that good? Like from the thing?
Yeah, it looks good.
You're given N lines. Yeah, that's perfect. Where G is the amount of gold that is produced in the first day, and D is how much gold it diminishes each day. And M lines, you're basically given A, B, T. A is mine, some mine number between 1 and N, since we have N mines, same as B. And T is the number of days to go from mine A to mine B. So how can we model this as a programming problem we can solve with a computer in an efficient manner? That's the question. I'll probably keep it there for a few seconds. Well, we can start by looking at the input, which is actually a graph of mines. I can draw the first sample test case just to show how that looks like. You can have this. That's the problem for the data. Thank you. Alright, so the input for one of the test cases will be as follows. So now I'll draw the graph that they basically give you in the last few lines. You have two mines. So mine 1 and mine 2. And then the number of days it takes to go from mine 1 to mine 2, and from mine 2 to mine 1 is 2 days.
Which line is that from?
This is from this line.
That one, okay.
Good question. Now we are given, we have to work with this input side, input. Mine 1 starts with 1 gold on day 1, then it produces 0 gold on day 2. Mine 2 produces 10 gold on day 1, and then produces 5 gold, and then 0 gold. So we can see we start with 10 and keep subtracting 5 every single day afterwards. I'll say this is t equal to 1, since it's the first day, t equal to 2, and then t equal to 3. From the problem statement, we're told that we start at day 1, on day 1 at mine 1, and then we can go any other mine we want at any given day. We just have to take t number of days to go from mine I to mine j. Now the problem, we want to maximize the amount of gold we can get. We can take the amount of gold on any given day, and then once we leave that other day, we can go to another mine. So what approach can we use to solve this problem? Well, the first approach, should I ask questions?
Can I take like a hint? Or
go ahead.
a jab?
Yeah, take a jab.
Like my guess so far is that we have to construct a DP table, where potentially the columns is the days and then the rows the mines.
Okay.
But I haven't figured out, well, yeah, no, I haven't figured out, like, I know you have to look back. For example, if you're in the second mine, and I know you have to look back a certain amount of days to see how much you can build up for that day with mine 2 plus mine 1, but I haven't like fully structured it.
That's a great start. So it is a DP problem. This is a DP lecture, and we want to basically, if we can start off, I always like to start off with a brute force, a recurrence solution, and then go from there. Because memoization, for my mind, makes a lot more sense than tabular method. So we can write a recursive formula. First, I'll go through the basics, understanding of the algorithm, then we'll go into code. But let's just draw a graph that we haven't been given, just any random graph. Can you see that? I'll label these based on the mine numbers. And the problem statement doesn't say that this graph we're given is a tree, so we can even have cycles in it. 1, 2, 1, 2, 3, 4, 6. Alright. So from this graph, let me move this. There. Awesome. So from this graph, we always start off from mine 1. We can see this as a starting point, and we can choose to go to either mine 2 or mine 5 from there. And it takes, we'll just call this T1, T2, T3, T4, T6. It'll take T1 days to go from mine 1 to mine 2, T2 days from 1 to 5. So we can basically keep track of the day we're currently in, starting from day 1 here. And then we add the number of days to traverse that path to this. So plus T1, or day 1 plus T2. Makes sense? Now we can actually do this all the way to the end, and the maximum number of days we can take, it's actually based on our input parameter, which is right over here. We can see how many days it takes for the mine with the most number of days to diminish, to go to 0 basically. And then that's the maximum number of days will actually be in the mines. Any day after that, we're only earning 0 gold, so that doesn't matter. We can't be there for infinite number of days. The input parameters matter a lot because it will determine whether a time complexity is correct or it isn't. So I'll write them right now. Alright, so from these input parameters, I think that's it. Oh, and T is less than 100. So what's the maximum number of days we can actually stay in any given graph at worst case? I'll actually ask that question to the class. So given these input parameters, what's the maximum number of days you can actually stay in the mines at absolute worst case scenario? Think of what you can make. So n is mines.
And then D represents how many days it takes to diminish to 0, or it gets cut in half.
It gets cut in. It doesn't get cut in half. It gets cut by this number D.
Oh, it gets cut by D. Okay.
So starting.
That's the subtractor.
Yeah.
Okay.
Got it.
And then it starts off with G.
Yes.
Okay. Yeah, start tracking. So 100.
No. So this is the days to traverse.
Oh. Oh, 1,000 maybe.
Yes, it is 1,000. So why is it 1,000?
So if it starts off with G is equal to 1,000, and
Mhm.
subtraction is just 1.
Mhm.
It would take 1,000 days for that to reach.
Awesome. Yeah, that's correct. If you start off with 1,000 and then you subtract 1, which is a possible case that they can give you, then it'll take 1,000 days for you to be in this graph. So absolute worst case scenario, you're in the mines for 1,000 days. Awesome. Let me start moving this. Now, since we're given a graph, usually you want to do some sort of solution that deals with some graph traversal, because it's important to keep track of the connections to each node. So what kind of graph traversal algorithms do we have? DFS and BFS. Those are pretty common ones. You have other ones, but yeah, those are the main ones. So for this problem, I like using DFS, so we're gonna look at the DFS algorithm and see how we can apply that to this problem. So I just read the pseudocode for DFS in a recurrence form. So with a recurrence call, we start at some given vertex. We say that it's visited, just to not go back to it. And then we iterate through its actual neighbors. Usually when we want to keep this graph in sort of like a adjacency list, instead of a, what do you call it? Adjacency matrix, just because the runtime and then the space complexity kind of blows up with a matrix. So this is us iterating through some vertex V, which is a neighbor of vertex V, where U and V are mines. If vertex V is not visited, and we can just recursively call the first search. And this is just the algorithm to search through the tree. So we want to actually use something similar to this to solve our problem. All right. We actually, let me see, does anyone have any ideas how we can do this? How can we translate our depth first search into a DP solution that works for this problem? I'll give you guys a couple minutes.
So we still want to check if it's already been visited, right? Because if we previously visited, that means that we got more gold that first time, right?
No, not necessarily. So we can actually, let's take a look at an actual solution. So we start at mine 1, we can actually go to mine 2 and then take T1 days. Then it could actually be optimal to go back to mine 1. Or it could be optimal to go to mine 5. But coming back to certain vertexes does not happen in our depth first search, but it can happen in an optimal solution.
Oh, you might want to so for here, for example, you might want to come back to 1 because T1 plus T2 might be less than T3. So it's better, instead of going from 1 to 2 and then 2 to 5, it's better to go from 1 to 2, then back to 1 and then to 5?
Yeah, that could be a solution.
Oh, okay.
So with DP, you always want to start off with, and I always do this, start off with a brute force approach. How can we try every single combination of paths that end on maximum 1,000 days, or for any given solution, the maximum number of days to diminish the last mine to 0? How can we do that?
So how can we brute forces?
Yeah. Just a general concept.
What if we remove the if statement, like if not
You
Yes.
keep visiting the vertices, but does this ever stop?
Oh,
There's no base case.
Yeah, there needs to be a base case.
Awesome. So what can we add to this to do that?
The days.
The days, awesome. So where would I add the days?
Outside of the for loop.
Technically yes, but we want this as a parameter
Oh, yeah, yes, yes.
to our solution. I'm gonna change this because it's no longer just a depth first search. I'm gonna just call it something generic like solve. So we added a parameter d for day, whatever day we're in at a certain mine. That's an important state of our DP. So what will happen to the number of days once we go to the next vertex?
It decreased by 1.
It will decrease by 1. Let's say we start at time equals or day 0. So let's not go from n, let's start from 0.
Oh, then add 1.
Add close, not 1, because each path has a different day.
Oh, right. Oh,
Just, it doesn't have to be code, just
Oh, okay.
plus, I'm just gonna say,
T of I.
that's fine.
oh, okay.
Wait, in code, in this adjacency list, will we have to keep track of that, like edge weight?
Yeah.
The list will be a tuple? Or
Yes.
here? Okay.
So instead of actually just taking care of an int, so I'll do it like how you're saying. So v, this is v, the vertex, and then d plus v dot, I'm gonna say days.
Oh, that's all I was wondering how you get the base. Okay,
Yeah.
There's, I guess, different ways you can keep it that.
So it's no longer just an integer we're storing in this adjacency list. We're actually storing a tuple, as Lazaro says. So let me see, where can I write this? So this is just an example how we'll store this in an actual computer. We have a given vertice, let's say 1, and then now we're storing where it leads to the path, so mine 3, and then the number of days it takes to traverse that. That's how we're calling v.vertex and v.days. So that's awesome. Now, how do we actually keep track of our answer in our recurrent solution? That's the question. Does anyone know?
So keep track of how much gold we have accumulated so
Mhm.
far?
Let's say you're in a given vertex at a given day, right? How much gold do you make that day?
Okay, wait. So for each vertex, we know how much gold it started off with,
Mhm.
and then D tells us how many gold is we subtracted per day.
Mhm.
So it would be G minus D times T, or the number of days so far.
D times.
Yeah, you have D there too, so.
Yeah. I'm gonna name this D1 and alright, so awesome minus D1. So that's actually right. So on any given day, or say D1, this is how much gold you're getting for that specific mine. Where G is the initial gold for that vertex, and then D1 is how much you're subtracting it each day. There is one problem with this though, which is, if anyone can point it out.
G.
No.
Okay.
Let's say this day is, I don't know, really big, greater than like 900. But our starting gold is only, let's say, like 9.
Oh.
Do you have? And then we decrease it by 1 each day.
Is that maximized between that or 0?
Awesome, yeah. So it's the max between this and 0. We cannot actually lose gold where we're in a mine. We can only gain it or keep it at 0. So this we can actually add to our code, our solution. G minus D times 1. So we can initialize our answer. Let me move this. Initialize our answer as this, since that's how much gold we currently have. Now, we want to update that gold after choosing a certain path. So how would we do that?
Wait,
Mhm.
So what if outside of this recursive function,
Mhm.
we initialize ans to 0, then every time we do ans plus equal that?
We just add equal to?
Yeah.
Let me think.
You mean
But-
recursive?
Oh, you mean,
It'll
'cause then
only be
we'll
increasing.
Go back and choose a different path.
Yeah.
Oh.
We can do this a couple of different ways.
Let me, I'm trying to like make sense of it in my head. So here, let's say we're starting off with 1, right?
Mhm.
We initialize an answer to be equal to that, and then we want to continue, and we want to find a path with our, of 1,000 days, starting on 1. We would need to pass ans, or return ans?
Which one is it? Alright, I'll give you guys a clue. So, for any given answer, ONDP, we have this thing called suboptimal structure. Basically, we can solve our current state with sub-problems that we already solved optimally. Yes, Mr.
Okay. Okay, so
Hmm.
here inside of the for loop, right?
Uh-huh.
We do ans plus equal solve v dot vertex d1 plus v days. And then outside of the for loop, before the answer, we initialize ans, we do if d1 is equal to 1,000, return ans. Actually, no, it would have to be after the answer, unless you want to redo the word.
Where do you put if D1 equals to? After ans?
Yeah, after ans, so, yeah, if d1 is equal to 1,000 days, just return ans.
Alright, does everyone agree with that? Alright, so this is technically a base case, which is correct. So we found that 1,000 days is the maximum number of days we can stay in the graph. Now, one little issue with this is that, let's say we're given a very small graph. Where G and D are very small for all vertices. Now we're actually waiting until 1,000 days for this small graph every single time. Let's say we're given 1,000 graphs of this size, very small graphs. We're actually taking a lot more time than we need for the solution that we already solved a bunch of days ago. Yes?
Can we also stop when we know that the goal rule to get from every minus be 0? Actually, no, that's what we're doing with the D1000. Yeah, never mind.
So it's actually how we solve this for D1000, we can actually solve it for each individual test case and keep track of that in that solution. So once it reaches this number of days, we can no longer get a better solution. So it's now 1,000 days. I'm just gonna say if D1 equals to number of max days, which we can pre-compute after the input.
Is this an example of pruning?
Yeah. Well, I don't know how you want to look at it. Pruning will be different, I believe.
Okay.
So let's look. This seems good. Let's look over here. So we're adding every time we solve a suboptimal problem. Does everyone agree with that? Alright. So it's not add equals. So that's a hint. So what else could it be?
And this is a totally random guess.
Mhm.
Is it multiply equal?
No.
Okay.
Alright. So we're running a little bit low on time, so I'll write more. So let's say there's another answer. We'll call this answer 1. And we initialized this to negative infinity. In practice, negative infinity doesn't really work. There's no infinity number on your computer, but you can set this to a really small number, right? And we want to maximize this answer. So once we found an optimal solution for this sub-problem, we just want to take answer 1 and then make it equal to the maximum of this answer or this subproblem. So this, at the end, we're going to have an answer 1, which gives us our optimal solution based on these other subproblems. It's not going to be all of them added together, because then you're not actually getting the solution, you're just getting a summation of everything. You're instead getting one of the solutions. Which path should you take? And now, after a for loop, after going through all of the vertexes, we're going to return our answer, and then we're going to add this optimal subproblem solution. So this way, we ran through every single path, stopped after a number of days, which is the maximum number of days, and then we got our optimal sub-solution. Now, can anyone give me an estimate of the time complexity for this solution? No.
N squared.
N squared? Way worse.
Way worse.
Yeah. So I'll start writing the recursive.
Big Allen times, right?
But that would be constant.
These guys wait for powers.
And to the end.
Alright, any final
And to the end.
end to the end, I think. So number of minds, oh, end to the end. So you're basically saying the number of minds and then end.
And then nine.
Closer, but no.
Into 1,000.
End to the dot, let's not use numbers, so we'll use the parameters we're given. It doesn't have to be a tight bound, so, alright, so I came up with, let's say we have n number of minds. So most at any given vertex, you're looking at n minds. And then, let's say you, the maximum number of days is, well, Lasser said 1,000. He actually was correct, but I wasn't gonna give it to him. So the max number of days, we can see that in our solution, we have n for each layer, and then the depth of this is gonna be the max number of days. So n to the max number of days, which is, I believe it's like 1,000 to the 1,000. So this never runs in our lifetime. We don't get the solution working in a contest. So how can we optimize this? We have a recursive solution. What can we do to make this run faster?
You said memorization.
Yes, memorization,
Because
awesome.
you have all those suboptimal problems,
Yeah.
I store them.
You want to store them since they're overlapping.
And
So let me move this over here. And the way we will do this is we have a DP table. It's actually size, you have our parameters here. So size 1,000, 1,000. For any problem, we don't have to, we can reuse this table. We can keep this as a global variable basically, and then reuse it. But this is the max number of size. 1,000 times 1,000 is well within our constraints, and then we can actually keep this. So this is good. But after, first, our solution to dp u d1 would actually be equal to this, and then we'll return this solution. So we store the actual solution so we don't have to pre-compute it, and now we add another base case. Let me, where did I put this? Usually in a practical standpoint, we can set this DP table to a value that will never be used. So in this case, like we can -1. We'll never have a solution of -1, at least we'll have it 0. So initialize this table with a bunch of -1s, and then after we check this first base case, if dp at u d1 is not equal to -1, means we already solved this subproblem, then we just return that. And this will be our final solution. This does work. I've tested it, I ran it, I coded it, and it does work. It does get accepted. So this is a general, it is a solution. but when you're actually programming this, there's a lot of small nuances that can go unnoticed. So you want to take care of those. And let me get the name of this. So if you actually go to this website, it's VJudge, right, Lazaro?
Yeah,
.com.
I think so. Is it that? No.
So if you go to vjudge.com and then you search for contest,
It's down there.
it's .net?
Yeah.
Oh, okay. It's .net. I called it treasure map. If you go to treasure map, you can find a contest with this one single problem right there. You can submit a solution. I highly encourage you to code this up yourself and then try to get an accepted answer. Because hearing this and then learning it is one thing, but actually putting into practice takes it to the next level. So that's the end of the lecture. Thank you, everyone.
Thank you.
Hmm? Oh, yeah.